Perfect, thank you. So first, thank the organizers for inviting me. And maybe before I start, so there is a card here for Tali Kaufman, who just had a baby. So if you want to sign it, and we're going to give the card to her. I think, where is it? Maybe later today or tomorrow. Okay, so this is a joint work with several people, with Eshan Chattopadhyay and Puya Khatami, and with my student Kaveh Husseini. And I know this is a mixed audience, so maybe many of you don't know this concept of pseudo-random generators, so I'm planning to explain everything that's in the title, and so basically that's a plan. So I'm going to start by giving a very quick overview of what are pseudo-random generators and why we care about them. And then I'm going to basically talk about the main new definition that we have here, which is some relaxation of this notion. And then I'll show one example why they are sort of easier to construct than the standard object that people study. And then sort of the main technical part would be how to reduce, how if you can construct this relaxed object, you can sort of use them to design the general object, if you know what they are or not. If not, then you'll see in a bit. And this is where the high dimensional part would come in. It would involve doing some random walks in high dimensions. Okay. And in general, I mean, it's a new area. It's a new, I would say, direction. And I'd be very curious to get your feedback on that. And I think there are many interesting open questions that arise from that. So what are pseudo-random generators? So in general, I mean, I'm guessing many or most of you have seen pseudo-randomness comes up in various contexts. And so if you have a distribution or random variable, then we say it's pseudo-random with respect to some family of tests if it sort of looks random. So if this family of tests cannot distinguish it from a random or uniform distribution, and this type of objects come up everywhere. You know, in graph theory, you can think of the regularity lemmas given some notion of pseudo-randomness where the tests are cuts in a graph, or in number theory, you can think about the Gauss uniformity norms, defining some other notion of pseudo-randomness, where now the tests are counting some patterns in numbers. And if you go to computer science, and if you want to try to de-randomize algorithms, and here the pseudo-randomness is with the tests being efficient algorithms and so on. So there are many, many different ways of defining pseudo-randomness, and it sort of depends on what's the context that you're trying to get. And here I'll be talking about a very specific context, which is that where we're trying to fool some family of Boolean functions. So from this point onwards, our tests are always going to be defined by some Boolean functions. So you're given a function from n bits to 1 bit, and you're given some family of functions that you want to study. And this family sort of comes from whatever context or application that you have. So in complexity theory, there are many families that we study that are somehow simple in various ways. And I'll give some examples, but for the most part, I'll be studying this question in the general sense. So there is some family of what you consider to be simple Boolean functions that you want to sort of try and fool. So what is a distribution here that's pseudo-random? So it's very simple. So it's some distribution, a random variable over Boolean input, so plus minus 1 to the n. And we say it's pseudo-random with some error parameter epsilon for this family if the following things hold. So you take any Boolean function in your family, and you ask, well, what's the average it gets over truly uniform inputs? What's the average gets over sort of pseudo-random inputs coming from your distribution? And it should be roughly the same, up to some small error. Okay, so and the question is, can we sort of find this type of random variables that are somehow efficient? So this is where pseudo-random generators will come to the picture. So again, these are just copied everything from the last slide. So a pseudo-random generator is just an efficient way of somehow sampling this random variable. So what do I mean by sampling? So we will have some small amount of true randomness, maybe r bits, and then a pseudo-random generator will take this small number of r bits and somehow stretch them into n bits, and n should be much more than r. And what we want is that this type of distributions should look the same to whatever class of Boolean functions we're trying to fool. Everything here is sort of very generic and abstract for now. And sort of ideally what we want to minimize what's called the seed length, so how many truly random bits we'd like to get here, and also we'd like G to be somehow simple. And in complexity theory, given various types of families of functions, we have different techniques how to construct these pseudo-random generators. So I just want to give a couple of examples. So here's one example that probably many of you have seen, which is this notion of k-wise independence. So here we're thinking of functions on n bits, but that only look on k of the bits. So it's some subset of all functions, of all Boolean functions. And what we want is to find some distribution that looks uniform. In fact, here we'll ask for the error to be exactly zero. So it should look exactly the same as a uniform distribution. And this is sort of, we know the answer. This is what's called k-wise independent distributions. And the optimal seed length unit is k log n. And these are sort of tightly related with questions in coding theory. So they are basically, so constructions are based on codes with sort of large minimal distance. So what's that? So I explained, I think, so seed length, well, thank you, is this parameter r. The seed length is how many truly random bits I need to give you so that you can stretch them into many more bits that look random for your bounded family of tests. Of course, if your test is all Boolean function, then you cannot do anything. If your test is some subset that is simple enough that hopefully you can stretch things some more. Thanks, Yuval. So this is maybe one basic construction. Here's another basic construction. They're called small bias generators. So here the tests are just characters of z2 to the n, or in another way of saying it is, remember my variables are plus minus 1, so my tests are just products. So it's all possible products of a subset of the variables. And again here, what we want is some distribution that has small support or small seed length that looks random to this type of tests. And again here, this has been well studied since the 90s, so this started by Naor and Naor in the 90s. There have been many, many more works on it, and we know that the optimal seed length is order log n over epsilon. We still don't know what the right constant here should be, but up to constants. Not here, the question? Oh, okay. So this is just, again, if you've never seen these things in the past, then these are just two basic constructions that we have that we like to use. But you know, usually what we're trying to study are classes of functions that are more rich than just functions on k bits or functions that use these specific characters. What do we do then? So, you know, we have all these sort of classes that we like to study, where we say that a function is simple if there is some easy way of computing it. Like, for example, if there is a small Boolean circuit computing it, or if it's computed by some low-degree polynomial, or other models that we think are simple. And the question is, can we use these sort of basic constructions, like k-wise independence or small bias generators, to fool this type of class as well? And in general, the answer is that people have developed, you know, along the years, several techniques to construct pseudo-random generators, and they usually fall into one of two buckets. Either it's realizing that you can take these basic PRGs, and even though they're supposed to fool basic tests, they actually have more power than what you initially expected, so they can fool richer classes of tests. That's one example. That's like a very lucky situation to have. The more common is that we start with this basic PRG, then we combine, then you sort of can combine them in sort of clever ways and get more general generators that fool richer classes of tests. And what I want to talk about today is that it sort of falls into this second general category, but somehow by relaxing the notion of what we're trying to construct. So now, okay. So I want to define, so maybe, okay. So now I want to define a new object that I like to call fractional PRGs, that, and I'll explain what it is in a second. It somehow tries to solve a more relaxed problem, and because of that, it's sort of easier to construct generically. And then the main question will be, can we sort of use this to construct what we're actually trying to construct? So here, let me start with an alternative viewpoint of PRGs. So you're starting with some Boolean function, and let's for now assume that there's just one Boolean function we're trying to fool, which is sort of not a very realistic situation, but for the sake of the argument, assume there's just one Boolean function. So let me take this Boolean function and expand it into its multilinear extension. There's always a unique multilinear polynomial computing it. And actually, I'll only be caring about inputs that fall inside this sort of Boolean cube. So then the function maps bound the cube to values between -1 and 1. So you know, if this is originally my Boolean function, that now inside the cube it interprets its values. To the solid cube, yes.
How do you extend it?
So it takes the multilinear, the Fourier expansion, okay. Okay, so now it's inside now the function is defined inside the solid cube. And now here's I just want to sort of, as a starting point, give you a different way of looking on what is a PRG, what are pseudo-random variables. So I'm going to use both of those interchangeably. So basically, I want to argue that if I have a random variable, x, it takes values in the vertices of the cube. And what we want is that the average of these vertices of this function should be very close to the value it gets in the center, f of 0. So why is that? Because f of 0 is just the average of the function over all the points. Okay. So maybe here's like a pictorial way of thinking about it. So we have our Boolean function, which is these blue values. And if you average them, then we have 5 1s and 3 minus 1. So the average is a quarter, unless I made a mistake. And then maybe this red is my pseudo-random distribution, which only takes 3 values, and let's say probability a third each. And if I average that, I get some other value, a third, and there's some gap. Okay. So, but this should be the pictorial viewpoint of what we're trying to construct. So forget about the definitions. What we have is we have this n-dimensional cube, and there's some values written on the vertices, which are this Boolean function. And what we're trying to find, and we have a family of those, and what we're trying to find is a distribution, which is this red distribution, which should be very, very sparse. But on the other hand, if I average for every Boolean function in my family, if I average it over these red points, the average should be close to the true average, which is again the same as the value the function gets at the 0 point. So now let me sort of define this new object, which will look very, very similar. So again, a PRG just takes values on the vertices of the cube. And now I want you to allow to take values also inside the solid cube. Okay, so now we're going to break away from the standard notion of PRGs. Now my fractional PRG can take values inside the solid cube. Okay, so we can do more. So it's a more general object, but the requirement is again the same. So you want the values that we get here, if we average any Boolean function in a family of these values, should be close to the value you get around 0. What? Oh, that's a very good question. So there's, like Klim is saying, there is always a trivial solution here, which is just x is always 0. So soon we're going to need to get rid of this non-triviality. We want to get rid of the triviality. But for now, notice this is a trivial construction here. Now, if you allow this trivial construction, this is very easy to do. But somehow, this will not be very useful. At the end of the day, what we'd like is to say, if you can construct that, and it's somehow not trivial, then you can use it to construct an actual PRG that gets Boolean values. So somehow getting always 0 doesn't really help you in that. But for now, we also have this trivial solution. So this is the main definition I want to study. So is this definition clear? Okay, so the only change I made is that now I'm allowing my random variable to take values inside the solid cube, not just on the vertices.
So what is the family of tests that you are pulling?
Some family, I don't care what it is.
So here the definition is only for a particular function.
For the function, but if you have a family, then I want that for every function in this family, this should hold. So for PRG, I want it to get Boolean values. For this fractional definition, you're allowed to take fractional values. Yeah, I wouldn't care really what this family is, for the most part. Okay. So maybe here's again a pictorial viewpoint. So now my red distribution, my pseudo distribution, takes values inside the solid cube, not just on the vertices. Okay. So now there are two interesting questions to study here. First of all, is this actually useful? I mean, is it somehow easier to construct this if I allow you to take values inside the cube and not just on the vertices? Okay, that's one question. And the second question is, if you can do it, can you use them to then construct actual PRGs that take actual Boolean values? And the answer to both would be yes. So I'm going to show you a construction, a generic construction that works for many, many classes of interest. And then sort of, the more technical part would be how to use this to design an actual PRG, and the way to do it, as you'll see, will be to view this as defining a random walk inside the solid cube. Okay. So I want to now address these two questions. So let's construct them. I think that would be, I'm going to show you basically the one construction we have that is sort of, it's pretty generic, but on the other hand, it's sort of also very specialized. So I mean, I think an interesting question that comes is, can we cover other constructions that look different, that use the fact that you're allowed to take these fractional values? But let me show you one construction that we have. Okay. So what I want to show you, so I'll give you formal definitions in a second, but basically, we're going to look on Boolean functions that have some certain structure, because we need to assume something. I'm going to assume that they have bounded Fourier tails. I'll define what this means exactly in the next slide. But somehow it means that the Fourier tails don't grow as extremely as they could go for random Boolean functions. And in that case, and the important thing here is that for many classes of interest that we study in complexity theory, we can prove that they have bounded Fourier tails. And somehow this is one way of putting them all in one big box. And somehow there's some parameter that controls the tail behavior, and this parameter changes between different classes, but there's going to be just one parameter that you have to carry out. Not about a...
What sits on the high levels or on the low levels?
Okay, so let me give you the exact definition in the next slide. Okay, this is okay. So I will just jump in ahead. Yes. So this is... Okay, let me give you maybe what I write as a technical definition, and then you can ask the questions, okay? I think this is going to answer many of your questions. So here's going to be my definition of bounded tail. So we have a Boolean function, we have the standard, Fourier coefficients of it. So what's the requirement here? That if you look on the L1 at the level k, it doesn't grow. It grows exponentially with k, but where the exponent is something that might be small. Okay. So this is one way of looking on bounded Fourier tails. This is the L1 bound.
And C is less than 1.
No, so C is not. So if C is n, then that's the worst case. If C is 1, you're basically very, very anywhere between 1 and n. So it could depend on n. It could be an absolute constant. It could be whatever. It's some parameter.
I guess it would be why you're summing and not averaging, and then it would look nicer.
What's that?
It would look nicer if you're averaged over the level k, not sum.
And then it would be you have to divide by n choose k, right? I agree. You can do it in different ways, but anyways, yeah.
So this is definitely L1 or so.
This is L1. Okay, so the one. So I know many people here. If you know this type of tail bounds, and typically people study L2 bounds, and maybe I'll use the board here to write. So L2 bounds, which are more commonly studied. There's no space here. Yeah. So the L2 bounds imply L1 bounds. That's the point I want to make. So the L2 bounds that are more usually studied. So L2 bounds. So in general, Parseval. Oh, it doesn't write. Oh, okay. Okay. So L2 bounds. So it's good. Perfect. So Parseval tells us that that this normalization, because it's a Boolean function, the sum of the Fourier coefficient squared is 1. And then an L2 bound for the Fourier tail will be something like the sum of f hat s squared. If the size of s is more than k, decays fast, somehow like maybe 2 to the minus, let's do k over c. Okay? So again, there's some parameter c here. And this basically is up to level c. When the side of the circle you see, you get roughly maybe half the mass, and then it starts decaying fast. And this is maybe the more commonly studied notion of L2 bounds, but this implies L1 bounds for Boolean functions. So this L1 bounds is a weaker property. So the proof is it's not elementary. It uses the fact these are Boolean functions, but it is still true. So the place where I learned about is this paper of Avishai et al. From a few years ago. It might have been known before also, but so linear Matsuri-san proved L2 bounds, right, for AC0, and we have other techniques prove L2 bounds for other functions. And then in general, when you can prove L2 bounds, they also imply L1 bounds. But there are other.
Okay, so when it says on the slide that it includes Boolean functions
with L2.
Included in the class.
Yes, I mean whenever you have L2 bounds that decay exponentially fast, you also have L1 bounds that increase but not super fast. And the C here and the C there are the same up to a constant. Okay. It implies it, yes.
It
Implies. The L2 bounds imply L1 bounds. Thanks. Good. But the other direction is not true. I mean, there are functions control L1 bound and not control L2 bounds. Okay, so let me assume this controlled L1 bounds because it's easier to work with. So now I want to give you a general construction that sort of fools any function with controlled L1 bounds. So I'm going to start with one of these basic constructions I described in the first part of the talk of small bias generators. So this is, again, it's a random variable, call it y, that lives on the vertices of the cube, that fools all these characters. And then I'm going to do the following thing, that's really going to use the fact that I'm inside the solid cube, I'm going to shrink it. So now I'm going to find my new random variable is going to be, take this random variable and just replace every 1 with p and every -1 with -p, just shrink it down to by a scale of p. And p is going to be some parameters that depends on the control that you have on the Fourier tails, and like roughly 1/c is what you need. So now, if I started with some small bias generator living on the vertices, now I shrink it to live on the vertex of this smaller subcube. And what I claim is that this fools any Boolean function that have controlled Fourier tails. So the proof is actually very simple.
Is this just the analog of applying noise? Like
It's not. It's actually not quite. It is related to applying noise. It's more related to applying random averages than applying. But it is there are relations.
what was the difference between a random average?
It is like applying noise, but when you view applying noise, you usually think about you start with the vertex, you go to some neighboring vertex under some noise distribution, and here I want to do this taking values inside the cube. But I mean, mathematically it's similar, but I want to view it differently.
You start with small bias generator and then you get another small bias generator?
Well, it's the same random variable, just the values it takes is not 1 minus 1 to the n, it's minus pp to the n. So now it doesn't take Boolean values anymore. So I want to get something that's fractional.
Yeah, but do you get something better parameters now?
It's the same thing. I get a different object. Okay, so now it takes values inside the cube.
Now he's fooling something else. The small bias generator.
The small bias generator fools characters. Yes.
Ah, I see. You start with
For-
Different
okay.
Yes. So this fools characters, and I claim this fools any function with control tails, but somehow it takes these fractional values.
It's very useful to say that when c goes to infinity, you get the trivial.
Yeah, well, it's not even infinity. So when c is n or poly n, but if c is log n, then you get something better.
So you're saying essentially you're pulling like 1 when c is 1, when it's character, and when 1 to shrink and full. Yeah.
You fool more, but also what you get is somehow a more general object. So, and if you want at the end to get a distribution on the vertices, then it's not clear how you start with a distribution inside the cube and go to a distribution on the vertices. So this is somehow the more interesting part, I would say.
If I see the point of this minus e to the n, I take the harmonic extension. Don't I just find the noise operator?
It is. No, I get it. The analysis is exactly applying the noise operator. Yeah, but I want to view it as taking as a distribution that takes values inside the solid cube. So again, what I want to argue is that basically, again, so this is I'm just copying everything from the previous slide. So the constructor, we have a function with control tail. So the sum of the L1 of the level k grows like c to the k for some parameter c. We start with a distribution that's small biased, with error, let's say epsilon, and we just scale it down. And I claim that there's enough space here to actually give you the proof for why, with a small enough font at least, but not that small actually. Why this fools anything? So it's a very simple fact. Just like James said, just basically noise operator. This is the proof. So let's just go through it. That's the only actual computation I have in the talk. So let's just go through it, just to do it once. So what are we trying to see here? So we have my function on this random variable, and I want to show that it's close to the value it takes at 0. So I want to bound the gap. So I can take my function, expand it to all the Fourier coefficients. So this would be the 0 Fourier coefficients. So I need to bound the contribution of all the rest. So here's the sum of all the rest Fourier coefficients that are not empty times whatever value my random variable x gets on this parity. And we just use sort of here's just triangle inequality. And now here's a place we're actually going to use the fact that we're shrinking the values that are not minus 1, 1. So why is this shrink down value of x with parameter p? So if I look on a character of size s, I get this sort of p to the s factor into it. And and now we get basically the value of y on this character, which is by assumption at most epsilon. So basically what we get here is this summing of all Fourier coefficients of the absolute value times this sort of exponentially decaying factor. And because we assume, and now if we group the Fourier coefficients based on their size, then we assume when we use this assumption, then everything just, is just geometric series. So everything is very, very simple. So what I want, so this is just one construction. What I want to use this as just to illustrate it by allowing a pseudo-random generator, random variable, take fractional values. It becomes much, much easier to fool classes that previously required much more complicated analysis to fool. But on the other hand, you get this more general object. So the real question is, can we use these fractional PRGs to actually construct PRGs? So this is like the main thing I want to show you, is how we can use fractional PRGs to actually construct, Boolean, valued PRGs. Yes. Yes. Yes, very, very simple way. Okay. So basically, the message is somehow if we start with this basic PRG of small bias generator, and we just scale it down, now it fools these very general classes of functions. On the other hand, we sort of take these fractional values. So now the next step I want to show you is how we start with anything. It doesn't have to be this specific one. Any distribution takes fractional values, and we use it to construct another distribution that takes Boolean values. Okay? And here will be one place where we need to assume non-triviality, because this could just take the value 0 always, in which case this should not work, right? So somehow we need to assume that something here is non-trivial.
So the challenge now is some kind of rounding.
Yes, exactly. Exactly. So now I want to do this sort of. There will be rounding, but actually the main thing here is we're going to view this as performing steps in some random walk inside the solid cube that converges to a vertex. And ideally, it should converge fast to a vertex. So so we have this sort of non-triviality assumption where we say, wait, what if x is always 0? So I'm going to enforce some non-triviality, which is going to be that every coordinate in x has some non-trivial variance. Okay, so if you look on the agreement, x is a variable with n coordinates. So on the variable, every coordinate should have some non-trivial variance. Okay, so that's going to be my assumption. That I don't care what construction you give me, but every coordinate should have some non-trivial variance. It should not be always 0. Okay, so just to make sure that we're on the same page, so in this special case that we had before, where x takes values in minus pp to the n, so if I also enforce that the average is 0, but let's say multiply with a random bit or something, then the variance is p squared. Okay, so in this special case, it's p squared, but I will not be assuming from now on this special case. I will just be assuming that every coordinate has some non-trivial variance. Okay. There was a question? No. Yes. Okay. So we need one more assumption. So up until now, I was talking about one function, but in general, we're going to have a family of functions, and I also need another condition on this family of functions. It's going to be a very natural condition. It will be that this family of functions should be closed under restrictions. So if you give me any Boolean function in this family, and you fix some of the inputs to be -1 or 1, it should still be in this family. Okay, so most families satisfy this criteria. Okay, so is this definition clear? So I will always be working. What?
In a certain sense of
Well, most studied, let's say. So, yeah, but I'll still be viewing them as having an input, you'll just be ignoring some of their inputs because they're fixed. Okay? Yes?
It's a little bit ambiguous. So if you're talking about polynomial depth circles, so once you restrict to something which is polynomial size.
No, so that's a good question. Let's say my function is computed by a polynomial size in n. So all I would say, if you take a variable x1 and set it to 1, it should still be a polynomial size circuit. No, so the parameter is still n. The function is still on n bits. So I don't change the number of inputs. That's a good point. The function is still on n bits. I'm just taking some of these bits and fixing them to constants, some of the inputs. But I still want to view it as a function on n bits. So the parameter n doesn't change. That's a good point. So even though I fix some value, the number of variables stays the same. Just the new function ignores some of its inputs. Yeah, so all these classes stay the same. Nothing really changes. Okay. So that's going to be the only two assumptions I'm going to make. So here's the main theorem that we prove. So let me go through it carefully. So again, what are the
Your definition from the previous slide doesn't satisfy.
which one?
Take a function where the variance in every coordinate is at least some constant.
No, but this is my fraction. No, but when,
That's a natural definition. It doesn't fit. I'm only complaining about the word natural. Essentially, every natural family.
okay, but maybe my natural would say is, so if you take the function that we study, that we're trying to fool, like bounded depth circuits, or linear threshold functions, or bounded degree polynomials, or TC0. All these things have this type of behavior.
Can we agree on many interesting examples?
Okay, good. Some interesting examples. Let's agree on some interesting examples. Good. Anyways, so here's the setup. So we have a class of n-variate Boolean functions, so which is closed under restrictions. You somehow constructed for me this fractional PRG that fools this class, but it can take fractional values. And this fractional PRG is not trivial in the sense that every coordinate has some variance P. Then I claim that there's a generic way of taking this and converting it to an actual PRG. It gets Boolean values. So what we do is, and I'll show you the details in a minute, so we need a few samples from this random, not just one. So we're going to use this random to design a random walk inside the solid cube. And we will need t steps, but t will not be too bad. So it will depend on this noticeable parameter by 1 over p, because basically p is going to be the step size. And it will depend on the dimension logarithmically, which to me initially was surprising, the fact that you can converge fast in logarithmic time. But anyway, you take t copies, and there is some explicit function that you're going to see in the next 10 minutes that's going to take these t copies and use them to design a random walk that converges to a vertex. And the error that you get here is not too bad. If you started with error epsilon and you have t steps, you basically only lose epsilon times t. Okay. So this is a theorem I want to show you.
Why were you surprised by logarithmic time? You're touching every coordinate in a step.
Yes, but somehow you want to convert, you want all the coordinates somehow to converge to a plus minus 1 solution. I don't think that in other random walk type algorithms, you need to pay poly n time to do the random walk. Like if you think about other random walk type that are not related to this type of.
Not in continuous time, which is what you're doing here. You're touching every coordinate perfectly.
I am touching every coordinate, but it's not clear that. Okay, anyways, it does. You can think whether it's surprising or not. It's a question. To me, it was surprising.
Do you have to x to be in the 0, 1, minus 1, 1, or you can take it outside?
No, minus 1, 1. Minus 1, 1. So it's not allowed to go outside the cube. Yeah, it's not allowed to go outside the cube. When you can think what you do, it can do it, but for now, no, it's just inside the solid cube. So, okay, so the seed length you need is basically whatever seed length you needed for this fractional PRG times basically log n factor. Okay, so how do we do it? So let me sort of, anyways, let me skip that for now. So how do we design this? So the first thing to realize is that you can think of this fractional PRG as doing the first step in a random walk. So the first step we know how to do. Why? Because what is this fractional PRG? Just take some values inside. So now I moved from 3 dimensions to 2 dimensions because it's easier to draw. So now I'm in this sort of n-dimensional, where n is 2, I guess. And we have this sort of small distribution here. It takes values inside the cube. And the promise is that for every function in my class, the average on this point is the same as the value in the center. Okay? So this is going to be the first step in my random walk. And the question is, what do I do next? How do I define the second step? Because the way I define it is just to approximate things around 0. But now, now when I'm going to come to make the next step, I want to try and, let's say I moved here. Now somehow I want to approximate the value here. So I want to do a random walk around this point. So how can I massage this object to do a random walk around an arbitrary point? Okay. So now, okay, so these are the generic questions. So we did this random walk. We made some steps. Now we reached here, and some point A in the cube. And I want to use this fractional PRG to define a random walk around this point that would, that would look like the average would be like the average here. And also it should never go outside the cube, right? We never want this random walk to go outside the cube. We want to always stay inside the cube. So it took us some time to realize how to do it, but at the end the solution is very simple. So here's what you do. You take the largest subcube that is centered at this point. And then you take whatever your random variable x is, just scale it so it would fit here. And my claim is this is going to work. So if you use this, now notice that somehow as you get closer to the boundary, your steps in this direction become smaller and smaller. And on the other hand, they never go outside the cube. So at least this part we're guaranteed, they never go outside the cube. And my claim is that this is still good, you will not incur too much error here. So maybe just let me define this in a bit more formal way. What do I mean by restricting X to a subcube? I mean, so this is what I mean. So let's see what we're doing here. So we're at some point A, and I want to look on the maximal subcube. So I want to look what's the distance between this point and the boundary of the cube. So basically, so for every coordinate, let's say for the first coordinate, I want to look at the value a1 and ask what is the absolute value of it, and what is 1 minus that. That is the distance of the first coordinate from the boundary, and the second and third, so you get some vector, delta A. And then let me also use this notation where x circle y, just a pointwise product. So this is going to be the random step. So we start at A, and we use the random variable x, but then we scale every coordinate with the appropriate scaling so that it stays inside the subcube. And then the claim is this still works. Just under this assumption, then also doing this step will incur an error of at most epsilon.
But you don't increase your error to the end?
So the error, if I do t steps, the error will be epsilon times t.
Ah, okay.
But the behavior of t on epsilon is much better, so you can sort of should if
Not increasing speed.
you're not really increasing it too much. Okay, so that's
This is completely obvious from the assumption. No? That
so it's not. So you need to. So this is where you need the assumption that the family function is closed under restrictions.
I see.
So it's not. If you just for this one function, it won't be true. Yes. So now let's define this full random walk. So we start. So we choose some independent samples from this sort of fractional PRG. So what's going to be the random walk? So we start. The first step is just use x1, and then in general, if at step t I ended at coordinate yt, what do? I compute the largest subcube which should fall, and I sort of use x. I guess this should be xt plus 1. And I use xt plus 1 to make the next step. Okay, that's it. So it's very simple. And then the last step is somehow at the very end, you want to get some Boolean values, right? So what should we do? We should say, well, you do some number of steps, and then you want to round. Like you said, so how do we round in the obvious way? So you take the last place where you reached, and if it's positive, you map it to plus 1. If it's negative, it's minus 1. You do it for every coordinate independently. So you do this very natural rounding. And again, the theorem here is that you don't need too many steps for this rounded version to converge so that the error is not very big.
So there's nothing random about this random walk.
There is random in the sense that each step comes from this fractional PRG, which is random. Remember? So let me go maybe one step back. So these are random variables, right?
Okay, so
So you do have random variable, but just sort of take this to fractional values. So this is the only source of randomness. So
You
give,
apply it independently.
yes, and you apply it independently t times. Yes. Okay. So this is the theorem. So I want to give you some.
and
Yes.
one question, do you really need the excess be noticeable or the average of the variance?
No, so you didn't every. So let's say all the coordinates were noticeable except the first one. Let's say the first one is always 0. Then if you do this random walk, it's all going to stay 0. So you didn't every coordinate to be noticeable. Yes. Yeah, good question. Okay, so why does this work? So I'll give you some hints about the proof. So first of all, why do the individual steps work? This was what Nati asked. So basically, it works because if you take your function, and let's take the function restrict to the subcube, it's another, not Boolean, but bounded function. Turns out that this bounded function is in the convex hull of restrictions of your original function. So if you can fool all the restrictions, you also fool everything in the convex hull, so you fool this subcube function. Okay, that was part 1. So part 2, which to me was the more surprising thing, is why do we converge fast? So we're sort of trying in n dimensions to converge, but we only need log n steps. So why is this true? So the lemma is that if you make, again, this number of steps, then with high probability, all the coordinates, all the n coordinates, you're going to be really, really close to the boundary, 1 minus epsilon. And the reason is really a one-dimensional phenomena. It's because of polarization. So what is polarization? Polarization is basically the following fact. If you look on this random walk in every coordinate, it's a one-dimensional random walk. It's a martingale, but it's a bounded martingale. And bounded martingales polarize very fast. In exponential time, they converge to the boundary. Which is why even you're in n dimensions, you only need log n steps. Okay, so this was maybe part 2 of the ideas. And part 3, the rounding, this is pretty straightforward. So if you're really close to the boundary of a Boolean function, if your distance to the boundary in every coordinate is epsilon over n, then you just do the rounding, you don't lose too much, because you're super close. And you can get to be super close because this random walk polarizes very fast. Okay, so that's it. That's basically, the rest are details. Okay, so maybe before, so I want to basically, so what have we done so far? And I want to spend some time talking about open problems, because I think there are many open problems that arise here. So I gave you this new definition of this fractional PRG that gets these fractional values inside the cube. And I show you this one example where for many classes that people have studied, you can give this very simple construction that fools all of them. But then your distribution has to take fractional values and necessarily takes fractional values. And then there's this generic reduction using a random walk that takes these bounded random variables and makes them converge very fast to a Boolean value, PRG. And then basically, for the applications that for many natural classes that people have studied, this gives you a generic PRG that fools all of them. So AC0 and low degree polynomials and linear threshold. So many classes get fooled by this. Sometimes we get comparable seed lengths, some cases we get much better ones. But to me, the nice thing is there's basically one construction that works for all of them generically. So well, a lot of previous works were sort of tailored for specific classes. So no, so in finite fields, this still doesn't quite give you that. I mean, oh, so parity would work. So this will give you a different construction for parities. I mean, but then you will not start with a small bias. You start out even weaker than that. What's that? That's less clear. I mean, so there is a technical question here is where, so let me just go back to this sort of definition of these bounded tails. Let me sort of go back here. So even before AC0 parity, where is this? You can ask, which function classes satisfy this type of condition of the L1 bound? So low degree polynomials over finite field, let's say over F2, don't satisfy the L2 bound, but we conjecture that they do satisfy the L1 bound. So you can prove it by hand for degree 1 and 2. And for higher degrees, we can prove a slightly weaker bound. We can prove k to the k bound. And we conjecture that you get c to the k bound. So if this would work, it will give you some alternative construction for those, which then you might try to use to get to AC0 parity, which we don't know how to fold. Currently, we don't have any pseudo-random generators for AC0 parity. So that might be an approach. What's that? Okay. Okay, that's good to know. Yes, I mean, so one question, general question is what function satisfy this type of L1 bound, which is weaker than the L2 bound? Now let's sort of skip ahead again.
If this is satisfied by ACC2,
Yeah.
this given you way to separate ACC2
It will give you a PRG for it that we. So majority doesn't satisfy it. Yes, it will give you, in fact, for ACC2, so this is circuit. So this is even harder. But even for ACC2, we don't have average case lower bounds. I mean, I'm saying we don't even know it for polynomials. We don't even know it for polynomials. Even for just which is the subcase of ACC2, right? F2 polynomials of constant degree. Even then, we don't know if this is true. We conjecture it's true. If it's true, maybe, I don't know. I don't want to conjecture. Maybe, I don't know. It's a different approach. Okay, if Gil wants, I conjecture it. Why not? To make Gil happy, why not? Okay. So now I want to give you 4 other questions that I think are interesting, which is how can we use these ideas, which I think are still preliminary, to better understand this random walk behavior and the value of these fractional PRGs. So the first one, I want to give you a different way of viewing this type of construction, which actually generalizes many other constructions in the literature, which is that of a gadget type of construction. So here's one way of viewing what I showed you in this talk. So I can put the things as a matrix. So every row in this matrix is one of our steps in the random walk, and they're independent. So in this specific, they will take values, between -1 and 1. And then on every column, so the rows here are independent, and they should come from something simple. And then you apply some function to every column. And this function in what I showed you was this sort of random walk type function, where we start doing the random walk on every coordinate. And this controls how things behave, and then you do some rounding. But I want to make the argument that many of the constructions in the literature look like that. So you start with some basic objects in every row, maybe small bias generator or something like that. And then you apply a careful gadget on every column and get something. And we have several constructions that look like that, but the analysis is sort of very tailored to every specific case. So the first question, which at least to me is very interesting, is can we find some systematic way of analyzing these types of constructions? So again, if you know, for example, there's this sort of very nice work of Manuel Viola that said if you want to full degree D polynomials over F2, you start with rows that's full degree 1, which is just a small bias, and you XOR them. Why XOR? Why not something else? Why not taking majority? Why not doing whatever? I don't know. So the analysis we have is very sort of specific. So again, I think that's an interesting question to understand. Also for the specific construction I showed here, so this random walk is this very, again, it's nice, but it's a very weird gadget. It's not this nice symmetric gadget. It's not even symmetric. Can you do something much, much simpler here, like majority? Like sum the values and see if it's positive or negative. I mean, I don't know if it works, I don't know if it doesn't work. It's unclear. So can we analyze these types of construction in a more systematic way? So that's one question, let's say, or two questions. The other one is about sort of improving the parameters here. So I showed the construction I showed you needed this type of steps in the random walk, and I conjectured you actually need maybe this plus that, but more generally, can we choose steps that are not independent? That's one good way of usually improving the randomness you need in a construction. Can you make the steps be only somewhat independent? And there are different techniques in the literature how to do it. We tried, we failed, so I think that's an interesting question to try and explore. What? Expander walks, or K was independent, or all the usual tricks we have. So we don't know how to use them, but maybe. So our analysis actually requires the steps to be independent for that to work. The other approach is to say, what if my function class is simple? So it's not some arbitrary function class. I assume something more. In this case, you can show that you can terminate the random walk faster. You don't need to walk that many steps. So the only case where we know how to prove it is this very extreme case where all the functions have low sensitivity. So if the functions have low sensitivity, and again, let me not define it, but if you know what it is that you know, then you can replace this n with the maximal sensitivity of the functions. But that's a very extreme case. So we don't know in general how to improve this. Last question. So I showed this one construction of this that takes, that actually uses the fact that you can take fractional values to give this new construction, but it's just an existing construction scaled down. Now, I didn't show you, but I'm arguing that you can take several existing techniques in the literature, like random restrictions, random averages, and put them in this framework, and it gives you a much cleaner way of analyzing them. But I'm trying to find other ways, other things we could do by taking fractional values. I mean, for example, your random walk could take the value 0 on half the coordinates. It just should not always be the same coordinates. It will be other coordinates. As long as you somehow make every coordinate have somewhat of a non-trivial variance, it's okay. So it's unclear whether you can use this. And the last question has nothing to do with Boolean functions. You're just asking, so in this specific case, we're working in n dimensions, and we want to converge very close to the boundary, but we only need roughly log n steps to do it. And the reason is the analysis is about this bounded martingale that polarizes very fast. Now, there are many types of random walk-based algorithms that people use. So here I wrote some examples, volume estimation in high dimensions, or MCMC types, or discrepancy minimization. In all of them, as far as I know, the number of steps has to be polynomial in the dimension. And my question is, under some assumptions, you can use this polarization effect to reduce the number of steps from polynomial to logarithmic, or to subpolynomial in general. So I think that's
an... You do a random walk at continuous time on discrete cubes, it will converge in log n time.
Yes, no, I agree, but the question is, can you use this to speed up some algorithms? I mean, all the others I know here use...
No, but saying that it's polynomial in a dimension, it's not the correct... I mean, here you're it your way, it's a mixing time log n.
Yes. No, I agree. I fully agree. Yeah. So I'm asking if you replace a cube with something else, can you still show somehow? Like, for example, in discrepancy minimization, all the algorithms we have require polynomial number of steps. But maybe you can do better. I don't know.
I mean, every analysis is based on a log sub-level inequality. That is fine.
Anyway. So it's a generic, yeah. Okay. So that's it. Thanks.